Bye.
Hello, everyone. I'm going to wait maybe just like a couple of minutes for other people to arrive because there's only 17 of us and normally there's a few more than that. Yeah, it's week 9. Yeah, it's week 9. I wasn't really kind of expecting to be doing every week after the Easter break because I didn't check the schedule because I'm an idiot. But we are doing every week after the Easter break. So our tutorials are over and you just get more me. Yay. Well, anyway, so this week is week 9. I'm still going to wait maybe a minute or 2 more for other people and also for them to go out so that I don't have to listen to that. And we're going to do question 2, question 4 and possibly question 5 from sheet 9. And the reason I have picked these 3, I have picked question 2 because I think if we can do question 2, then we know the difference between when the variance is known and unknown, and we know pretty much everything that we need to be able to do confidence intervals. Question 4, I'm doing a special request. I don't know if it's for somebody in this class or one of the other classes, but somebody emailed me saying number 4 looks difficult, so we're going to do number 4. And number 4 will give us a kind of idea of like if we change the sample size or if we change the degree of confidence, what kind of impact is that going to have on the size of the confidence interval. And question 5 is kind of interesting because it sort of does things the other way around. So rather than say we've got a sample of size 100, how big is the confidence interval? This one's going to say how big do we need to make the sample size to give us this degree of accuracy in the confidence interval. So, you know, that one might experimentally be really useful because it can give us an idea of how many data points we want to gather in order to have a certain level of precision. I've just randomly left somebody outside, which terribly sorry for leaving that person in the waiting room for like 3 minutes while I ramble. Sorry. Okay, so let's crack on and we'll see how we do. Okay. So I'm going to just switch to the visualizer. I hope you can see it. It's really bright in my kitchen today. So if there's any problem with any glare or anything like that, just let me know. I'm not convinced I will be able to do anything about it, but at least then I will know that you can't see what's going on. Okay. As always, if I start rambling or I say something wrong or you just got a question, stick it in the chat or unmute yourself and yell at me. Totally happy with that as well. Okay, great. Right, here we go. Looks like it's not. So, question 2. Oh, yeah, question 2. Question 2 gave us some information. It gave us 30 pieces of data. And it told us that we want to find some confidence intervals. So we were given that n is equal to 30. And we were also given our data which would allow us to calculate the mean and the standard deviation of the sample. In part A, we were told, suppose that we know what sigma is. Sigma squared we know is 30. And we were asked, what is the 95th percent confidence interval? 95% confidence interval. So this one we should kind of know. Oh, somebody else waiting. Okay, so this one we should be fairly confident with because it's similar to the ones that we were doing last week. What I'll do to start us off is if I give you the value of x bar and s squared, maybe you can just take a minute to have a think about what you would put in the confidence interval as the bounds, in the case 95% confidence interval. So using the data that you were given, you've got x bar is 52.2817 and the standard deviation is 34.69. And what you want to be careful with here is when you find the standard deviation that you use the one that's unbiased, so the one that's got the factor of 1 minus m, 1 divided by m minus 1 on the front. So that one, not necessarily feeling confident writing it any other way at the moment. Okay, so we want to use that one, the one with m minus 1. We've been told that we know what the variance of the sample is 30 in the question, and we want to find the 95% confidence interval. So we did some questions like this last week, and we saw that they were linked to the normal distribution. So let's just have maybe like 2 or 3 minutes just for you to give that a crack with those two numbers there. And try and decide what needs to go in the confidence interval. You should have nearly everything that you need. And we've just had that hint as well that it's to do with the normal distribution. So you're going to possibly need some kind of number that's derived from the normal distribution. So I'll give you a little second with that, and then we'll move on to part B. Okay, so I want to sort of get us started with the formula. So we need our interval centered on the mean. So I'm going to have x bar minus something and plus something. And it's going to be the same thing in both cases. So the factor that I put in is sigma divided by square root of n. And then z 1 minus alpha divided by 2. And the key difficulty here is, first of all, does alpha need to be, and where do I find z? So alpha is what's left over from 100% here. So it's 5%, 0.05 in this case. So if we substitute that in, we're looking for z 0.025. And this thing by definition solves put it into the CDF of the normal distribution. 0.025 equals 0. This one. Okay, and we can look up that Z in the table. One point 96 in this case. Now you find that, you know, we only use confidence in. Oh, 9. Yeah, Pedro's saying I need to do it the other way around. Now I do need to do it the other way around. I do indeed need to do it the other way around. So yeah, 1 minus alpha is. I've got to do the 1 minus. Just looking at my own notes there, thinking, well, the distribution is symmetric, so it shouldn't matter too much, but you know, let's stick with the way around that Sarah Louise is doing it. Okay. All right. So we're in that situation. We've found the number that we're going to need for Z, 0.975, 1.96. We're going to find that we only use certain values of alpha, so there's usually like only certain values of Z that come up, but they're certainly not worth memorizing. Just give them a look up in the table. So with that in mind, we now have everything that we need to plug it in, and you should just be able to plug it in along with the other values that we've been given, that I've given you there, to find the confidence interval. And you're going to get 50.32 and 54.25. Okay. So the next part of the question, B, says, well, what happens if we don't know what sigma is? So what about if sigma is unknown? Now, in this case, we've sort of, I mean, the obvious thing to do is to just take the previous confidence interval and you replace the sigma by S's, because we've estimated what the sample variance is. So just take the square root of this and stick it in. That's not quite right. We need to change what's going on with the Z to accommodate the fact that we're using an estimate for S. So we need to switch from using the normal distribution to the student T distribution. So the 95% confidence interval for the mean is kind of similar, right? So we are going to have X bar and then S divided by square root of N, and T okay, great stuff. And this one, you know, we should just be able to substitute in as well. Now the question is where to find that T, that value of T. Now, one complication we've got with student T distribution is in your table, you've got different degrees of freedom available. And you need to know which row to be looking at to find the right value of T, or which table to be looking at. Whereabouts in the table to be looking at. So what we need to do is we need to find this T for n-1 degrees of freedom, because we've got 30 elements in our sample, and we needed to modify by n-1, so we need to look at the 29 degrees of freedom. So we will have T 0.025 is going to be 2.0452, this one. So hopefully that's got us in the direction of just being able to plug that into this one for a confidence interval for the mean. We've got something else that we need a confidence interval for, though, because we don't know what the variance is. We're also going to have a confidence interval for the variance. And this one, again, has another one of these additional distributions that you've got tables for, and it's got the chi-squared distribution in. So the confidence interval for the variance, sigma squared, is we're going to have n minus 1 s squared, and we need to divide by chi squared 0.975. And then for the other end of the interval, we've got the same on the denominator, but on the numerator, we've got the other end of the distribution. And it's kind of important that with these two, that it's not a symmetric distribution. So if I know what one of these is, I need to actually look up the other one separately as well. I can't like say, oh, it's the same. It's, you know, we're not in that situation where things are symmetric. So we can look those two up. So chi squared 0.975 is the point at which chi squared 29 distribution, so 29 degrees of freedom in the chi squared distribution, which is 0.975. So where in the cumulative distribution of the chi squared 29 distribution, where you've got to the point when you've passed 97.5% of the values, and similarly chi squared 0.025 is again relates to the chi squared 29 distribution, and we need it to reach 0.25. So we need to take the point at which there is 2.5% of the distribution that's been covered. So with these two in mind, you can look up what those two values are. You should have got 45.7223, and then this one 16.0471. And you can just use those to calculate the values that go in here, because now you've got everything that you need. There's nothing that we don't know what the value of is here. So what are the differences? When we knew what the variance was, the confidence intervals based on the normal distribution, we can find those values that we want just by looking them up in the table for the normal distribution. And what we're rescaling by, so you know what we're standardizing by here is relates to the variance that we actually know. So hopefully you've had quite a lot of practice with those, because they've been popping up this week like crazy. They were also on last week's as well. The one that's new for this week is when we don't know what the variance is. So when we don't know what the variance is, we've got a very similar kind of form, but we've got our estimate for what the standard deviation is in there. And we have to move to student t distribution because of having to estimate S, we need to use degrees of freedom as 1 minus the number of elements in our sample. And again, we've looked those up in the table. But we also, in this case, need a confidence interval for the variance. Confidence interval for the variance relates to the chi-squared distribution, and we need to be really careful there that we look up those two values separately, because it's not a symmetric distribution. Okay, so that's just like stressing where the main differences there are. Now, it may sound a little bit ridiculous, but when I first encountered these types of things, the main difficulty I had was looking up the right value for Z, T, or chi-squared in the table. And I think it was just, you know, time pressure of exams, or just not really kind of getting the underlying structure of what was going on, that for some reason that was just the bit that I had a lot of difficulty with. So you might want to try and take as many of examples like this as you can. There's loads on this week's sheet. There's probably some on the past papers that you can look at as well. And, you know, really just spend as much time as you can like looking up, you know, the values that you need. And you know, find out basically where your weakness is with it. It might be no problem for you at all. It might be absolutely fine. Or you might feel like I did, and just be like, well, I sort of know what I'm doing, but I'm always looking up the wrong value. And if that's the case, you know, try and like go through a couple of examples very, very carefully, so that you can, you know, pick up on wherever it is that you're making an error there. You can always talk to, you know, either me or Sarah Lise in more detail about, you know, where you're going wrong if you are finding that you're accidentally looking up the wrong value. Okay. So we're going to move on to question 4, and with question 4 I'm going to leave it a lot more open. The first thing we're going to do with question 4 is we've been told that we've got a sequence of random variables x1 up to xn, and we've been told that they're all normally distributed with parameters mu and sigma, and we don't know what mu is, and we do know what sigma is. And just to make your life easy, later on we'll assume a value for sigma, but for now not. So the first thing I want you to do is, you know, assuming that we've got, that we're looking at 100 times 1 minus alpha percent confidence interval. Write down a formula for that confidence interval. Okay, so Louisa said, how do we work out S? So we should have be able to calculate what S squared is from the information in the data set, which we're going to use the unbiased version of an estimator for the variance. So we're going to use the formula 1 over n minus 1, and then etc. So we can just take the square root of this one, so square root of 34.67, and substitute that in where we've got S in the confidence interval for mu, and also the confidence interval for the variance as well. It's no problem. You know, I'm sure, you know, first of all, it's not a problem to have missed something. I feel like I went quite quick there. You know, secondly, if you ask, probably about 4 other people are thinking exactly the same thing, so it's fine. In fact, it's very much appreciated. So going back to what we were going to be doing here, so write down 100, the formula for a confidence interval for just any factor alpha, and have a think about what factors in that equation that you've written down could change experimentally. So what could you decide to change? So I'll point out one to you, and you know, we'll see what you know, what other factors might be in there. So N is something that we could change. We could take more elements of our sample. So have a look at the formula for your confidence interval and just think, well, okay, N is something I could change. If I increased N, what would happen to my confidence interval? And there's a couple of other factors in there as well that you could change. If you change to those, or if they naturally changed, what would happen to your confidence interval? I'm going to give you 5 minutes to just have a think about that. Try and remember what formula you're going to be using. Look at each of the individual factors that are going in there, each of the individual values that are going in there, and think, if I increase this one, what's going to happen to the width of the confidence interval? And then we'll go through together. Okay, so welcome to the one extra person. I'm very sorry if I left you sat outside for a very long time. Sarah Liz is recording, so if you want to catch up at a later date with the little bit of the class that you've missed, you're more than welcome. You're also very welcome to stay for the first part of the next class, because I've got class directly after this one as well, and I'm just going to do exactly the same questions. So, yeah. Okay, so I hope you were picking out the formula with the Zs in and with sigma in there, and then taking a look at that, what could possibly change. Now, the first hint that I gave you was that we might want to pick n, and if I make n bigger, then the square root of the positive part, the square root of n is also going to get bigger. So 1 minus square, so 1 divided by square root of n is going to get smaller. So the confidence interval is going to get smaller. The width of the confidence interval is going to decrease. Okay, so this could be something that we could control in practice. So we could think, well, all right, so I want to have a really nice big sample, maybe like 200, 1,000 kind of people, because or observations, because the more observations I have, the more precise I can be about what the actual mean is from the data that I've gathered in my sample. The second thing that could be changed there is alpha. And I want to say, well, what would happen if I increased, if I changed what alpha was? So I think the key, the thing that you might want to be doing is you might want to be saying, all right, rather than the 90th percent confidence interval, I want to be looking at 99th or 99.9, whatever else is going on there. So I could make alpha smaller. If I made alpha smaller, then what kind of impact would that have? Now, this one is a little bit more tricky than the others because I have to sort of think about what would happen if I make alpha smaller, what would happen to the z's. And if I kind of think about what the distribution of what the normal distribution looks like and where alpha is, so what I'm thinking about is having a little probability of alpha divided by 2 on this tail of the normal distribution and alpha divided by 2 in this little tail of the normal distribution. If I make alpha smaller, then these values of z are going to be pushed outwards. I'm going to get bigger. I'm going to get bigger, and the width of the confidence interval is going to, I should get smaller. Okay, so the changes the width of the confidence interval, and the confidence interval gets bigger. So if I want to be, if I want to have more certainty that the actual value of the mean, is inside the confidence interval, I need to make the confidence interval bigger, just in case, I've got a kind of quirky kind of sample. So if I want to be more confident that the actual mean is inside my confidence interval, I need to, extend it a little bit, like it's going to make things a little bit bigger. So that's what's going on there. Move alpha down, the z values go up, and the confidence interval gets bigger overall. And the final thing that could be changed would be what the variance, what the standard deviation of the actual data is. Now that might not be something that we can impact directly, but it might be something that we want to consider. Well, okay, so if I've got 2 sets of data, I know one is more variable than the other. What kind of impact is that going to have on my confidence intervals? So if the standard deviation is bigger, then I can be less certain about my data because I know that the variability is bigger, so the width of the confidence interval is going to increase. Okay. So in the second part, we were asked to populate a little table, and we were asked to also graph the width of the confidence interval against the number of elements in the sample for 2 different confidence intervals. So you were given alpha equals 0.1 and alpha equals 0.01, and then a number of different sizes of the sample, so n 5, 15, 30, 50, 100, and we were asked to populate this table. Now, if I give you that z 0.95 is 1.645, and z 0.995 is 2.576, we should be able to calculate the width of the confidence interval in each case. Now, the width is going to be 2 times the factor that we need to add or subtract off the sample mean to find the ends of the confidence interval. Formula for the width of the confidence interval is going to be 2 times sigma z1 minus alpha divided by 2 and divided by square root n. Okay. If you assume, as you were given, that sigma is equal to 10, you should be able to populate that table moderately easily. So I'd like to give you maybe 5 minutes or so to do that. And then what we'll do is we'll come back and just maybe do one or two of those together and just draw the graph or sketch the shape of the graph briefly so that you can see where you're going with that. So just from what we've been given, it should be fairly immediate that we can multiply this one by 10, there's 16.45, and then just for each value along here, multiply by 2 divided by the square root of n, so 2 divided by square root of 15, 2 divided by the square root of 30, etc., etc., etc. So that would give us the value of this one as 8.49, for example. Similarly, when we come to the second row, what we want to be doing is we want to be doing 10 times this z. So we'd have 25.76 on the top of our fraction. I have 2 times that divided by square root of 5, square root of 15, etc., etc., etc. And you'd get the value of this one as 7.29, for example. Okay. Now, if you've managed to fill out the rest of the values in the table, you can see that for both alphas, as you increase the value of n, the values in the table are going down. And if we graph these, we see that they look a little bit like the graph of 1 over x. So we get something that looks a little bit like this. So this is the width of the relevant confidence interval. And along here I've got n. And we'll also see that when our confidence interval is smaller, the width is bigger. So this one is for the 99% confidence interval, and this one is for the 90th. Okay. So as I increase alpha, I'm going this direction. Okay. So just before you go, I would also just like to start us off on question 5. I'll maybe take a look at the first part, so the second part you've got an idea of where to start. And so we kind of wanted to do what we were doing for the other question in reverse. So we were talking about the 95th percentile in part A, percent confidence interval, so 95% confidence interval. So the Z we were interested in is Z1 minus 0.05 divided by 2. There's Z 0.975, as Pedro pointed out at the beginning of the class. And the value of this is 1.96, as we saw earlier. Now, what we've been asked to do is we've been asked to make sure that the width of the confidence interval is less than a certain amount. So the amount I was given that I've got as my upper bound is 0.02. I want to try and make the confidence interval smaller than this. So I want this to be bigger than the width of the confidence interval. And I've just seen that the formula for that is 2 times sigma Z 0.975 in this case, and then divide by the square root of m. Okay. Now I don't know how big this sample is, so n is something that I want to try and find the value of, but everything else I now know the value of. So if I plug everything in that I know the value of, okay, and rearrange for n, so which is going to imply that n is bigger than 0.196 divided by 0.02, and all of that squared, which takes the value 96.04. So this experimenter wants to take n such that this is the case in order to get the confidence interval the size that she wants. So she should take n is equal to 97 to achieve the size of the confidence interval that she would like. So she's going to have to go out and interview or do 97 experiments in order to get the level of precision that she's looking for. And if you look at part 2, you'll see that that one's asking you for a for the same size, but for a 99% confidence interval. We can solve similarly for the value there, but intuitively from what we saw in question 4, would we be expecting the value of n in the second part of question 5 to be bigger or smaller? So if we were asking for the number of observations she needs to make the 99th percentile, so the 99th percent confidence interval, the size that she needs, would she need to be making more observations or less observations? Now I've got votes both ways. So yeah, no, Carmel's decided that Joe is right. He's saying bigger. And I definitely agree with Jo. So if she wants more precision, she's going to have to go for a bigger number of people to be dealing with. So give that one a go in your own time as well. Other than that, I'll see you next week, because I'm now aware that I've got to do every week. Yeah. And I guess that's kind of nice, right? That we got theory all of the way to the end now, rather than art. But maybe I should learn art so I can teach the whole of this course rather than just the non-art bit. Okay, so bye everybody, and I'm going to get ready to do this all over again. It's exciting. Hello, so welcome to the early birds. Class is going to start in about 5 minutes. Well, it's not going to start in 5 minutes, it's going to start in about 7 minutes because I will sort of give people a couple of extra minutes to arrive. So settle in. I'm going to put myself on mute because I'm going to continue having a snack. And I'll come back when there's a few more of us here. It's week 9. I wasn't expecting to be here because I thought I was only doing the even weeks, but that's fine. I figured out what we're doing now. So we're going to do question 2 so that we can be sure that we know the difference between what we're doing when we know the variance and when we don't know the variance with confidence interval. We're going to do question 4 because somebody from a different tutorial actually requested that we do that one because they thought it looked a bit tricky and a little bit unusual. And we're going to do question 5 because it's sort of asking us to do things the other way around. And I think it's kind of like really kind of cements the ideas in number 4 and sort of like if we're able to do it, then it sort of shows that we actually understand the mechanics of what we've been doing all of this time with confidence intervals. So I'm going to put you on mute, continue eating my snack, and we'll be back in about 5 minutes. See you in a bit. Hello and welcome to the extra people. We're going to wait another 1 or 2 minutes just to see if more people turn up. There's about 18 of us at the moment. I think last week there was about 25, something like that. Plus I've not finished eating. Sorry about that. Anyway, so we'll wait another couple of minutes just for a couple more people to arrive. We've got 2 more people in the waiting room, so that's a few more towards the total. Once everybody's here and all kind of settled in and everything like that, we're going to be looking at question 2, question 4 and question 5. So if you've tried those, take a look at your solutions, see how you're going. I'm going to put you back on mute just for a couple of minutes and just finish eating. Okay, so let's crack on. It's week 9. As previously mentioned, I wasn't expecting to be here because it's an odd numbered week, but fine, we're all prepared, we're all great. We are doing some confidence interval stuff. We are going to do question 2, question 4 and question 5. I'm going to do question 2 because it's going to give us like a bit of a recap of what we're doing in the case that we know what the variance is and we don't know what the variance is. We're going to do question 4 because somebody who was in one of the other classes had a special request for that question because they said that it looked a bit more difficult. So I thought, well, if somebody thought that, then probably everybody thinks the same thing. So we're going to do that one together. And then we're going to do question 5, which I just kind of picked because I'm going to mute Sarah Lee. Okay. So I thought I'd muted Sarah Lee. Anyway, I muted everybody. That's fine. Good. If you need to unmute yourself and you want to talk to me, feel free to unmute yourself and talk to me. It's just thought we don't need to be listening to Sarah Lee's family life. Anyway, yeah, we're going to do question 5 as well, just because it's kind of connected to question 4, and it sort of will demonstrate that we know what we're doing if we can do everything backwards a little bit. So let's crack on. I'm going to try and keep my eye on the waiting room as well. But I was struggling a little bit with that in the previous session. Okay, so question 2. With question 2, we were asked to find some confidence intervals when we knew what the variance was and when we didn't. So just to start us off, with question 2, we were given n is equal to 30. We were told in the first part, in part A, we were told we know what sigma squared is, we know what the variance of the underlying distribution is, we know that it's equal to 30. And we want a confidence interval. for mu. Okay. Now, what we'll also need in order to get there is we'll need to know what the sample mean was and what the sample variance was. So sample mean in this case is 52.2817, and sample variance I'm going to calculate using the unbiased version, so the one that's 1 divided by n minus 1. This one. Okay. .67. So for the first part, we don't actually need what the variance is, but what the sample variance is, but we will need it in the second part, in part B. So in this case, this is going to be very similar to the example that we did at the very end of the class last week. What we've been asked for is a 95% confidence interval. So we know in that case that alpha is equal to 0.05, so it's equal to 5%, the bit that's left over. And we had a formula for the confidence interval in terms of a value from the normal distribution. So we had x bar minus, and then we had a standardized factor here, which was z 0.975 sigma divided by square root of n. And the same, but with a plus instead. So we've got the mean again, and then plus the standardizing factor. So we've nearly got everything that we need there. We've got sigma. We were told what it was in the question, and we were told that sigma squared is 30, so we can put square root of 30 in there. We were told we had 30 elements in our sample, so we're going to be able to deal with that as well. I've just told you what x bar is, which is kind of handy. You're going to be able to plug that one in, which just leaves the z as to what's going on with that. Now, what we denote by z with a number here in the suffix is the solution to a certain equation in terms of the normal distribution. So what we say z does is it solves this equation. So it's the value such that I put it into the CDF of the normal distribution and I get out the number that's in the suffix, so 0.975. So it's the point at which, if I'm looking at the CDF of the normal distribution, I've got 97.5% of the data smaller than that particular value. So I'm able to look up the Zs in the table for the normal distribution. And I need to look it up in the table for the normal distribution because there's just not a closed form expression for this that I can find the inverse of sufficiently. So I'll give you that one as well. Okay. So we should at this point feel kind of confident and ready to roll with this. We've got all of the values that we need and we can plug them into this equation here. So we'll have 52.2917 as the mean, and then I need to subtract off this value of Z 1.96 times the sample standard deviation. So this is sample the standard deviation of the underlying data, which is square root of 30, and divide by the square root of the sample size, which conveniently is also square root of 30. So we've now got everything that we need to plug into this equation for the confidence interval. And it gives us that we need to have 50.32 and 54.24, the higher end of the confidence interval. Okay. So the second part, I've been told, well, what happens if I don't know what sigma squared is? So clearly I'm going to have to change some things about what we do when we know what sigma squared is. Now, the key thing we're going to have to change is we're just not going to know what sigma is to plug it in here. So we're going to maybe have to rely on the sample variance instead of the population variance. And there's also going to be a change to this Z factor here. Now, we can't rely on the normal distribution anymore because we've got, you know, added complications added in because we're using S rather than sigma. So the formula for the 95% confidence interval for mu is very similar to the one for mu here, but I need to change some things. As I said before, we need to change the sigma to an S, but we also need to change from a Z here to a T, and the T notation we also switch from 0.975 to 0.025. So the other end of the tail, just because that's typically the information that we have available. So x bar plus, and then the same factor S divided by square root of m, and then t 0.025. So I'm able to T. It does something very similar to what Z was doing here, except for it solves the formula in terms of the student T distribution. I can look it up in the table as 2.0452. And where I want to be looking in the table for the student T distribution is with the degrees of freedom, which is the same as the factor n minus 1 here. So I'm going to be looking at the row that corresponds to 29 degrees of freedom in the student T distribution table. In order to find the value of T. So what I'm looking for is a value of T such that I'm looking for a value of T in the table for the student T distribution such that when I put that value of T into the cumulative distribution for the student T distribution, I get out a 0.025 as the solution. So that's where I'm getting that value there. Okay. So the other complication with when sigma squared is unknown is that I'm not only going to want a confidence interval for mu, I'm also going to want a confidence interval for the standard for the variance as well. So I'm also going to want a 95% confidence interval for sigma squared. I didn't need this before because I knew exactly what the value for sigma squared is, whereas in this case I don't. So I'm going to need to have some kind of idea of what range it's in. And the formula I need for that one is n minus 1 again, because that's what's featured in my the estimate that I used for the variance. And s squared, and what I need to divide by is chi squared 0.975, and on the top end of this I'm going to be dividing by the other end of the distribution. Of the suffix I'm going to be using is 0.025. Now, unlike with the normal distribution, which is symmetric, I'm going to need to look up both of these separately because the chi-square distribution is not symmetric. So I'm going to need to look those two up in the table. And they do something very similar to what the t's did and what the z's did. So they're actual numbers such that if I put it into the chi-squared distribution with 29 degrees of freedom, I get the point out at which 97.5% of the data is bigger than, is smaller than that point, and also the point where 2.5% of the data is smaller than that point. So just to summarize, from the table you can find chi-squared 0.975 to be equal to 45.7223, and I'm looking for the 0.975 point of the chi-squared 29 distribution. And similarly with the other end as well. So it's a constant. I'm looking for chi-squared 0.025, which has the value of 16.0471. And again, I'm looking for the 0.025 point of chi-squared 29 distribution. Okay. I think the key part here, or the bit that's, if there's a bit that's tricky, the bit that's tricky is finding the right values of t and chi-squared and z from the relevant tables. Certainly that's the bit that I struggled with, especially under exam conditions when, I took a similar course to this many years ago. And I think where I was struggling was just, trying to decide what needed, what value I needed to be looking for. And the way that Sarah Lees has used the notation, so he's put in the suffix exactly what you're looking for here, does kind of aid you in that a little bit. The other difficulty is thinking about what the degrees of freedom are in each case, so making sure you're looking at the right row, and also, if you have any problems with transcription, so if you have a problem with like looking at a number in a table and writing it out, and like so maybe a couple of the digits like kind of switch on you under pressure, that's something to be careful with as well. I realise that, obviously not everybody's going to have the same experiences that I do with that type of horror show. But, just be careful. If there is anything that's difficult, it's looking up the right values of chi-squared t and z respectively. Okay. So moving on to question 4. The first thing I'd like you to do is to just have a think about what the 100 1 minus alpha confidence interval is going to look like. So what is the formula for this? What variables? Okay, so this should be not too tricky. Oh, we've got 2 extra people. Okay. Okay, so welcome to the couple of extra people, and I'm very sorry to have left you outside in the cold. This is of course being recorded, so if I left you out there for a particularly long period of time, please feel free to watch the recording for the beginning part. If you've got any questions or you want to just ask anything about what I've covered so far, please feel free to contact either me or Sarah Lees about them. And never worry about turning up late. It's just good that you managed to get here at all, really. So what we're looking at the moment is question 4. I've just asked what's the formula for the general formula for the confidence interval, and what variables are there in this formula that might change depending on the data set that we've got or the experimentation that we're doing, and how does changing each of these factors affect the width of the confidence interval. So this should be really straightforward, given what we were talking about with question 2. So there's 3 factors in there. So just to start you off, maybe one of the things that you might choose to change would be alpha. What kind of impact is alpha going to have on the size of the confidence interval? And there's another couple as well. So I'll give you a minute to maybe just write down the formula, identify those 3 factors, and then maybe comment on each of those. So if I increase that variable or decrease that variable, what impact does it have on the size of the confidence interval? And we will go through that in a moment. Okay, so just in case you're getting stuck there, let's just remind ourselves from question 2 what the formula for this confidence interval looks like. It's going to look like the sample mean, and then I'm going to need to subtract off sigma divided by the square root of n, and then this factor z, 1 minus alpha divided by 2. And the other end of the confidence interval looks kind of symmetric. Instead of subtracting, I need to add on to the mean the same factor. Okay. Now, I gave you a little bit of a hint with what things might be, we might want to consider changing, or, might change between situations. And the first one we spoke about was alpha. So what happens if I was to change alpha? Second one I would say would be n. So the number of elements in the sample that I'm taking. And the third one would maybe be what sigma is. Okay, so just looking at sigma, because I think sigma is maybe the easiest one there. If I've got a sample with a bigger standard deviation, so if sigma is increasing, so if sigma goes up, then the width of this confidence interval is going to get bigger, because if this factor is bigger, the amount that I'm subtracting off and adding on is bigger. Okay, so that sort of makes intuitive sense. So if there's more variation in my data, then I'm going to need a wider confidence interval in order to have the same level of precision. The second factor here that we've identified as something that might change here is n, so that the number of observations that we're making. So if I were to increase the number of observations I'm making, maybe I go from an experiment where I'm observing 10 pieces of data to an experiment where I'm observing 100 pieces of data. I'm putting a lot more effort in. So increasing n is going to make the factor 1 minus square root of n go down, which is going to make the confidence interval get smaller, because this factor here is going to decrease. So if I'm observing more data, then the size of the confidence interval is going to decrease. I can be more sure that the estimate for the mean that I've got, so x bar is closer to the actual mean of the data mu. Okay. And the more complicated one is what's going on with alpha. So that might be something, where I'm saying, okay, so I want more precision. I want there to be a higher likelihood that the actual mean is inside the interval in question. So if I make alpha go down, then the amount of data that I'm leaving so the chances of the actual mean being outside the confidence interval go down. And how I can intuitively think about that is if I think about what the normal distribution PDF looks like this, then when I'm making alpha smaller, I'm actually making the area that I'm excluding at the ends of the distribution here. Alpha minus divided by 2, alpha divided by 2 here. I'm actually pushing those I'm making the amount of information in those tails smaller. So in order to do that, I need to move the point Z in question. I need to move them further out away from the mean. So if I make alpha smaller, then Z 1 minus alpha divided by 2 is going to get bigger. And this is going to mean that the confidence interval also gets bigger. So the intuition there is if I want a higher level of precision, if I want to be more sure that the actual mean is in the interval, I'm going to have a bigger interval. that's where that's coming from. The next part of question 4 that we're asked to do is we're asked to take a particular value of sigma. We're asked to say take sigma equals to 10, and you were asked to fill out a little bit of a table. So you were asked, we had 90% confidence interval and we had 99% confidence interval. So this one has alpha equals to 0.1 and this one has alpha equal to 0.01. And then for a number of different sample sizes, we were asked to find the width of the confidence interval. So for n equals 5, 15, 30, 50, 100. We're asked to populate this table. And I'm just going to do one of these with you, and then I'm going to give you, I think, at least 5 minutes, maybe 7 minutes or so in order to finish them off. So the one I'm going to give a go is this one here. So if n is equal to 50, the value I need to put in here is going to be 2 times. Now I want a 2 because I'd like the width of this confidence interval, and I'm moving this far away to the left of x bar, and I'm moving the same distance away on the right as well. So that's why I want to be multiplying by 2. And I want to put sigma z. And divide by square root of 15 because I've chosen to calculate at the n equals 15 one for you. Now, the only other factor you need to bear in mind is what this z is going to be. You've been given what sigma is, so that was 10. And if we look this one up in the table for the normal distribution, we're going to find that that is 1.645 50, square root of 50, and the value of this is 8.49. Okay, now with that in mind, you should now be able to fill out the top row of that table really, really easily, because all you need to do is just change the value of n in the formula here for the width of the confidence interval. The second row is a little bit more tricky, and I want you to have a think about what you need to change, and you're probably going to have to use your table, so try and have your table to hand. And I'm going to give you until 40 minutes past, so 7 minutes or so in order to fill out the rest of this table. And then we'll just sketch a little graph or have a little discussion about what the values look like and move on to doing question 5. And so somebody has asked me on the chat why I wrote 2. And I think that's quite a good question. So the point is that the confidence interval is going to look something like this. It's going to have X bar in the middle, and it's going to have X bar minus sigma Z divided by N here, and X bar plus sigma Z by square root of N here. Yeah. Now, the total distance that I'm interested in for the width of the confidence interval is all of this distance here, which logically is going to be this one minus this one, which is going to give me twice this distance between the edge of the confidence interval and the mean. This going to be X minus this end, and minus X bar minus okay. These two are going to cancel out, and it's just going to leave me with 2 times sigma Z. Now I've just taken the subscript of the n, and of course we need to consider which Z we're looking for, in this case 0.95. Is that more clear why I chose to write 2 there? Are we happy with that now? Fantastic. So the bit that was a little bit arbitrary was the choosing, what factor of sigma to put in, and if we had a different idea of what we thought sigma should be, we could just choose to put a different value of that in, and again we get some values out which would show the same kind of trend. So hopefully that's made that a little bit more clear. If you fill out the rest of these values in here, I'm just going to show the top row and then maybe one value from the second row. So on the second row, in 50 here, I'm going to have the value 7.29. And I've just put the actual value in there so that you can check your calculation. That is roughly right. Now the values along this top row here, it's going to be 14.71. The one that I calculated for you, 6.01, 4.65, and 3.29. So what we can immediately see there is exactly what we intuitively discussed before. So the width of the confidence interval, as the number of observations goes up, the width of the confidence interval goes down. So I can be more sure as the number of observations increases that the mean of my sample is going to be closer to the mean of the actual underlying distribution. The same kind of thing is going to be happening with the 99% confidence, the width of the 99% confidence interval. If I graph those, as Sarah suggests in the question, I get some curves which look a little bit like the following. So I'm going to put n on the x-axis, and I'm going to put the width of the confidence interval on the y-axis. And what the curves are going to look like is they're going to be going this way, which is sort of what this data is saying. It's saying, like, for small n, I'm going to have bigger, and then as n gets bigger, these values are going to be going down. So like that. Suppose this is the one for the 90% confidence interval. My next question would be, well, if I put on the one for the 99% confidence interval as well, would I be expecting it to be above that curve or below that curve? And from what we were saying before, we were saying, oh, if I want to be more confident about the mean definitely being inside my confidence interval, I'm going to have to make my confidence interval bigger. So I'm going to be expecting that one to be on the top. So if alpha equals 0.01, I'm going to be expecting that curve to be strictly dominating the one for alpha equals to 0.1. Okay. So fantastic. The final part, which we'll just try and squeeze in the last couple of minutes, was I wanted to try and look at question 5. And I'll just talk about how to do the first part. What we were given is we were given sigma as 0.05. And we were given somebody who was doing some experiments, and she wanted the confidence interval to have a width that is no bigger than so we'd like the confidence interval width to be smaller than 0.02. Okay. We were looking at, she was interested for part A in the 95th confidence interval. And she was wanting to ask us, so how many trials am I going to have to do? How many data points am I going to have to generate in order to make sure the confidence interval is this size? Sounds like somebody's upset. Okay, so the general formula for the width of the confidence interval again. So the 2 sigma z1 minus alpha divided by 2 and divide by square root of n. Now, n is what I'm looking for, and I want to make this value less than 0.02. Okay, now I should be able to find everything else because I've been told that it's the 95% confidence interval. I know that alpha is equal to 0.05. So this value here is going to be z 0.975, which we looked up earlier in the table. It was 1.96. So 1.96. Okay. And so then I've got everything here in order to be able to rearrange for n. Okay, so is going to give me n is bigger than 0.196 divided by 0.02, all of that squared. And if I calculate what that is, I get 96.04. So if she wants her confidence interval to be in this range, so to be nice and small, to be less than 0.02 across, she's going to have to do 97 experiments. Okay. So this sort of gives us an idea of where these kind of confidence intervals might be useful. So if I was designing myself an experiment and I'm like, well, I want to be trying to find this variable that I'm going to be finding, you know, the mean of this data, and I want to be fairly certain that, you know, that I'm within a certain degree of tolerance. I want to make sure, I want to be sure that it's correct to two significant figures. How many times do I need to do my experiment in order to make sure that it has that degree of accuracy? So that's exactly, how we can use these confidence intervals. Let's sort of reverse engineer them to decide how, best to do our experiments, to decide how big a sample we need to be taking. So with that kind of method, you should be able to do part B as well. Is everybody okay with that? I think I'm going to wrap up there. Thank you so much for bearing with me and for listening, and also for coming to class, after 5 o'clock as well. Everybody can go now if that's what they want. Feel free to hang around and ask any questions if you need to. We can go from there. Other than that, have a nice weekend. I hope you get out in the sunshine because it's absolutely beautiful, and I'll see you next week. And as I said before, it's every week now until the end of the semester, and I'm going to try and remember that. All right, have a lovely evening, everybody. Hello, Sarah Liz.
Hiya.
Hiya.
Are you done?
Yes, I'm done. Thank you very much for letting me use your account again and your room. It's very kind of you. And
yeah, pleasure. Yeah.
Thanks again for doing the class on Tuesday morning for me. I really, really appreciate it.
Yeah, no problem. Yeah. Take care.
Okay, I'll see you next week.
Yeah.
All right. Bye-bye.
Bye.